I've been programming and therefore also debugging in Matlab for a really long time. I'm not going to admit exactly how many years, but it is possible that I've been working in Matlab for longer than you have been alive. And so I have developed a strategy for debugging over time. It's a strategy that is not always perfect. Debugging can be a complicated thing to do, but this is my go-to strategy and it works most of the time. So I call this the FIP strategy, that stands for Find, Inspect, and Plot. And in this video, I'm going to show you this strategy. I'm going to explain to you how it works and why it is efficient and effective. And then I'm going to show you an example with actual Matlab code that has a few insidious bugs in it. Okay, so the procedure works like this. The first step when you get an error message is to find the source of the error, which I sometimes call the offending code. Now, this might sound like it's trivial, but it is not always so easy. Sometimes Matlab tells you a line number on which the error arose, but it's possible that that is not actually the line that really truly originally caused the error. So even if line 100 is what produces the Matlab error, it's possible that the error actually comes from, something that happened on line 40. Or sometimes the error message is produced by a subfunction, but again, the error might not originally come from that subfunction, but might come from somewhere else. Sometimes you have a line of code that is really dense and there's a lot of stuff going on. There's a lot of functions being called and variables being used on one line of code. So even if you've identified the line of code, that still doesn't necessarily tell you the piece of code, exactly which code is causing the error. Okay, so the first step is to find where the error is actually coming from. Then you want to inspect, that's the next step. So the first thing to do is to look at the error message or the warning message that Matlab is giving you. Now, some programming languages have really awful, indecipherable error messages. Matlab is actually great in this respect. I think it is one of the best programming languages in terms of giving you helpful, useful error messages. So there's certain keywords that you can look for in the error message. And what often helps is to inspect the sizes of different variables. That's usually your first line of defense for inspecting the error and figuring out what is going wrong. For example, maybe you were expecting a vector, but the variable turns out to be a matrix. Or maybe you're trying to squeeze a vector into something that only accepts a scalar. So checking the sizes will often give you insight into the nature and the source of the error. Now, it happens sometimes that the inspection stage is sufficient for you to figure out the problem and come up with a solution. If not, then you go on to P, which is for plotting. Now, plotting doesn't necessarily mean you have to make a line plot. You can also make an image of the matrix or a bar plot. The point is to try to visualize the results. You want to visualize as much as possible, as many variables as possible. And that's because you will often find that just checking the sizes and looking at the error messages sometimes helps, but sometimes it's not enough. You need to see what you are working with. This is also particularly relevant for when you have data that end up being NaN or INF, so some non-finite numbers. For example, if you end up dividing by zeros, then that's the sort of thing that you would not see with checking the sizes. So the sizes of the matrices can be correct, but if they contain NaNs, that can cause some errors in certain kinds of functions. And plotting will help reveal that there are NaNs or INF, so infinite values. Okay, so this is the FIP strategy. This is actually just a good mnemonic for remembering this thing. There's kind of two more steps here. You want to fix or change the code, of course. That's the whole point of debugging. You want to fix the code. And finally, it's really important at the end to take a moment to reflect and to think about the error so that you learn a lesson. And that is the difference between making tons of errors in the beginning when you're first learning and making few errors as you go along and gain more experience versus constantly making errors all the time, constantly having buggy code. So you always want to learn a lesson so that you can become a better programmer for the future. Okay, so it's, you could argue it's 5 steps, but FIP full doesn't quite, roll off the tongue so well. So I just call this the FIP strategy. All right, so now what we're going to do is switch to Matlab. I will show you one example of this strategy. All right, so here I have some code, and looking at it immediately, there's no obvious MATLAB errors. If you look over here to the right, you see there's a green box here. There's no warnings, there's no errors. That would be different for if we just had an incomplete line of code like this. Now you can see this box turns red because there's some error messages here. And if you look down here, you can see there's a red horizontal bar. It's a little bit small, so if you cannot see it on my screen, you'll be able to see it on yours. And MATLAB is telling me that there's an error message on line 4, and basically because this is an incomplete line of code. Okay, so MATLAB is looking through this code, and it says it looks fine to me. There's no obvious error messages in here. So I'm going to run this entire line of this entire cell by pressing Control Enter. And now we get an error. And now, depending on the version of MATLAB you have, you might or might not get a line number for the error. Older versions of MATLAB didn't actually tell you a line number unless you were running an entire separate function. Newer versions of MATLAB, I think this started with 2018, will actually tell you a line number here. Nonetheless, let's pretend like we don't know which line that error is coming from. So what I'm going to do, because this still happens sometimes, we have an error, we don't know exactly where it's coming from. So I'm going to run through and run this code basically line by line until we see the error message. So this is the stage where I am finding the error. So now I'm going to run all of this for loop. This actually violates what I just said to run the code one line at a time. Okay, so now we see an error message somewhere in this code, but we don't know where it is. So set this looping index variable to be 1, or whatever is the first point, which it is. And now I'm going to run through this, the code inside this for loop line by line. Okay, so this one runs fine. So it must be that there's this line of code. So this is one of the things that I mentioned. So now we've localized the error to this line 32, but look how dense this line of code is. There's all this stuff happening in here. And then, we're setting equal to something over here. So there's still multiple places where this error could be. Now, you might think of debugging by running through this code left to right. So ABS, and then mean, and then EXP. But that's actually the wrong way to do it. The right way to debug code to find where the error is coming from is to start from the innermost piece of code. So the innermost piece of code is generally the part of the code, the function or the variable, that is inside the most number of parentheses. So we want to actually start here. We want to start from the inside of the most number of parentheses. So now I'm basically just going to start running this stuff. So this is 0, which is a valid number. Maybe, if this were NaN or something like that, or if it were empty. So now we've run this and we don't get an error message. So now we go out one parenthesis. We go out one little piece of code. So the next smallest piece of code that we can move outwards is this. So this variable phases, that's what I created up here. You can see it's just random phase values. So it's uniformly distributed random numbers between 0 and 1, and then I scale them up to 2 pi. Okay, so now let's run this. Aha, and here we see the error. So array indices must be positive integers or logical values. So you can see what we're doing here. We are trying to get the 0th element of the vector phases. Well, no vector can have a 0th element in MATLAB anyway. Of course, Python starts counting at 0, but MATLAB starts counting at 1, just like normal human beings and probably most other intelligent life forms in the universe. Anyway, so in fact, although the error is technically happening on this line, the thing that's really causing the error is not this line of code. So that's a little bit deceptive. MATLAB is trying to tell us that the error comes from line 32, but that's not really correct. The error is actually coming from line 29. So the question is, why do we get a 0 value here? Well, to understand this, we have to think about what this line of code is even trying to do. So we have this helpful comment here, pick random points to sample. So basically what we want to do with this code here is sample a couple of data points, a couple of samples, phase values, randomly from this distribution of phase values. And so the way that we do that is by generating a random number between 0 and 1, so it happens to be 0.8 in this time, and then multiply it by samp I, so the ith index in this looping, in this for loop, and then we round that. So, and we need to round that because this is going to become an index. We're going to use that as an index here. Now, this is fine, except that when we round, we can get down to 0. In fact, when you round this to the nearest integer, it's going to go down to 0. So what we can do to solve this problem is change round to ceil. So now it's going to round up. This is for ceiling. I've discussed this function several times before in this course. So now we're always going to round up. So now the smallest possible value that we are going to get here is going to be 1. And we can try that here. This is probably going to be exactly 1. Yeah. And now we can run through it. And now this line of code, I think, is going to work now. Yeah. So you see, it was not so easy to find the error. It seemed like the error was on line 32, but that was really just the line that was producing the error message. The error actually came from line 29. All right, so now I'm going to try running this cell again. And so we get a blue line here, and then we get a ton of these little dots down here. Now, what is going on here? Why are all these values zeros? So we're still not getting any error messages, but this seems like the wrong thing because clearly we are indexing this as a vector. And in fact, if you look at this matrix, mean vec L, it is a matrix. So notice now I'm inspecting sizes. That's one of the things that I said you should do. I'm inspecting the sizes of these variables. So because this is a matrix, we can actually produce an image. So I'm going to create an image of mean vec L. And this matrix appears to be zeros everywhere. All these columns are zeros except for the very first column, which has large values, and then the values seem to get stochastically smaller as we go down, as we increase in this dimension here. Now, here is a case where there is no explicit MATLAB error, but I'm pretty sure that this is not what whoever wrote this code intended to do, particularly because we're using the plot function here. So let's see how we get here. So mean vec L, this actually gets initialized up here using the zeros function with one input, and that is just n. Now, these functions like zeros and ones and nan, they will produce, if you give one input, they will produce an n by n matrix, which is what happens here. In fact, we just want a vector, so we have to say n comma 1. Now notice that, and now I run it again, and now it's fine. And mean vec L, which is vector length, corresponds to just a vector. So now we get the right result. So we only discovered this by visualizing and by inspecting sizes of the different matrices. So I hope you found this video useful. I hope you try to use the FIP strategy when debugging your own code or other people's code. And just keep in mind that, I don't want you to follow this strategy religiously. It is my suggestion for a way to get started. It is not necessarily always going to lead to the correct result, but it has worked for me much more often than it hasn't. In the next video, I'm going to show you more examples in MATLAB of the most common programming errors that I have encountered in my own code and in my students' code. See you soon.